Are we out in the air, Josephine?
So now let's formally start this webinar. So welcome to a new webinar in this FibRe and Treesearch online seminar series. As usual, we have people here in Zoom, so welcome. And you can also follow us on YouTube on Treesearch YouTube channel. So we'll have proper introduction by our speaker. But first, I just want you to encourage you who are listening. If you have questions, we will have a Q&A session after the presentation. So you can use Zoom, you can use the Q&A function or the chat to type in your questions or raise your hand or whatever. And you on YouTube, just use the chat function and we will try to get your questions answered. So I leave the word to Professor Annette Larsson to give an introduction to today's speaker.
Oh, thank you. Thank you a lot, Josephine. So I'm Annette Larsson, and I'm a director for the FibRe Center that is located both at Chalmers and KTH. So it is a great pleasure that we, together with Treesearch, can have this webinar series. And now we have the pleasure to introduce you, Professor Alistair King. And we have studied your paper. You are really famous here in Gothenburg, at least. We know that you have been working a lot with NMR and also applied it for different lignin cellulose-based materials. And as far as I understood, that you were before at Aalto, but now you are at VTT. And
I was previously at the University of Helsinki,
okay,
but they're quite close by. So.
Yeah, and then now, but we look forward really to listen to your presentation. So please go ahead.
Okay, thank you very much. I'll just try and find my presentation again. Can you see okay?
No, you are in the wrong mode now, so you need to go over now. Perfect.
Okay, great. Thank you very much. And thanks for the invite to speak. I think this is a really nice kind of educational initiative, and I'm really kind of honored to receive this opportunity. I'm actually now working in VTT about 1 year. VTT is kind of like the similar business model as RISE. They're kind of emulating each other a little bit. So it's in between industry and academia, where they kind of take advantage of the novel findings in academia and then try and translate that into impact in industry through various kinds of innovations. And I would say they're very nice places to work because you get to see the kind of very fundamental work going to the long-term impact after industrial application and in society. So I highly recommend people to look for jobs in these positions. So I'm a principal scientist in the bio-inspired materials team. So that is Hannes Oralma's team. And essentially I'm dealing with the chemical modification of cellulosics, focusing very much on surface modification, whether it would be nanocelluloses or pulp or various kinds of shaped objects coming from pilot lines. Previous to this, I've actually spent something like 18 years in the University of Helsinki, in the same research group as Ilkka Kilpeläinen, and we've worked very much on development of ionic liquids and analytics and fractionation methods and processing methods for lignocellulosics. And this has been rather useful, as it turns out. This knowledge in ionic liquids has allowed for, let's say, innovations in analytics, never mind the amount of money that has actually been pumped into developing new kind of bioprocessing technologies. So, and I think what I would like to discuss today is a little bit about the kind of theory of NMR. This is important to understand relaxation mechanisms, which are very important in both solid and solution-state NMR analysis of polymers. So once we have an idea about this, then I want to go on to kind of show how we've actually resolved or increased resolution of analytics by applying these ionic liquid type materials or electrolytes. And then I will give at least one example on actually how this is used in an analytical sense. But yeah, I will start. So quickly onto the theoretical side. So if you look at the anatomy of a NMR spectrometer, and quite many of these images comes from Valtteri Mäkelä's PhD thesis. So he has produced a very informative PhD thesis. If you would like to check that out, it's published through the University of Helsinki. And essentially your NMR spectrometer, you have your magnet and probe, you have a preamplifier to amplify or attenuate the signal if need be. Then you have the console, which is dealing with the electronics and the signal generation and conversion into a digital signal. And then you have the computer on how to actually process your spectra. And basically the console itself, it's attached to the magnet through the preamp, and the magnet or the probe is actually more or less a tunable radio receiver. So you pulse the sample and then you listen to what is given off, the kind of radio frequencies that are given off. And in the console, you basically have very high quality and large memory amplifiers to mitigate electronic noise. And then you have of course, synthesizers and very fast switching to be able to listen to these signals that are, or to irradiate and then listen to these signals without introducing artifacts. So the spectrometer itself, or the magnet itself, is more or less, you have a probe inside a superconducting magnet. So this is immersed in liquid helium, which is boiling at about 4 Kelvin. This is cooled again with liquid nitrogen, so that the helium is not evaporating very quickly, because this is, of course, a very expensive component and needs to be replaced. Then, of course, we have a vacuum to keep everything cold. Everything's wrapped in mylar space blanket. And we need these kind of superconducting magnets to give very large magnetic fields to actually give us strong enough signal to noise and resolution. So the reason why this is that when you put nuclei with non-integer spin quantum numbers into strong magnetic fields, you get this kind of a effect, which is originally discovered for the electron, so Zeeman splitting. And you have an energy transition, and the energy transition is much stronger for much stronger magnetic fields. And you get a larger population of the upper energy levels when you have a stronger magnetic field. So ideally, we want to get as a strong magnetic field as possible to get as good as signal to noise and resolution. And when you excite these nuclides, you get a upper population of upper Boltzmann population of energy levels. And then when you stop exciting and relax, you get radio frequency waves that are given off. And this is the signal that you detect. The basic 1D experiment is that you essentially carry out a radio frequency pulse, which is typically a 90-degree pulse for a 1D experiment. And then you listen to the signal that's given off. So this is termed as a free induction decay signal. So it has only a certain lifetime. And then when you do the Fourier transformation to convert from the time domain into the frequency domain, so essentially you get a frequency map of the nuclei in the sample, you get these sharp signals. So where the relaxation is important is that actually if you have very fast relaxing signals, when you carry out the Fourier transformation, it's actually an artifact from the Fourier transformation that you get very broad signals. When you have a long relaxation, this is desirable because the longer the relaxing the signal is, the sharper the signal you get. And this, of course, means that you actually get much better resolution of the species that are in solution. And that in terms of specifying a sample, in terms of their chemical constituents, this, of course, is desirable because in certain cases you may get rather a large amount of peak overlap that are difficult to separate using simple methods. So this is basically an artifact of the Fourier transformation itself. So why is NMR important? So this term, Heisenberg's uncertainty principle, so this is commonly kind of referred to by many people as the reason why you get broad signals in NMR, but in fact, it's why you actually have very good resolution in NMR compared to other methods of spectroscopy. So if you consider particles, so we know from Heisenberg's uncertainty principle that we can't tell the momentum and the position, or the change in the momentum and the change in position of particles to any accuracy below Planck's constant over 4 pi. So if you consider this de Broglie particle as a de Broglie wave, then these terms translate into the lifetime of the particle and the energy of the particle. So that means that if you have much higher energy transitions, then the lifetime of your relaxation is much, much shorter. And that then turns into poorer resolution whenever you have your spectrum. And if you consider that UV spectroscopy is 2 to 10 electron volts higher than IR spectroscopy, or about 1 million times higher than IR spectroscopy, and again, then about IR spectroscopy, the transitions are about 1 million times as high as NMR. This translates into really rather long relaxation times, and when you carry out Fourier transformation, then you get very high resolution signals. So this is really why radio frequency spectroscopy, NMR, is so important. So when it comes to relaxation in terms of, let's say, small molecules versus larger molecules such as polymers, and then going to the solid state, you have two methods of relaxation. You have a T1 relaxation, which is a relaxation of the spins back to the ground state. And then you have T2 relaxation, which is a kind of a decoherence of the spins. And there is quite a well-known relationship. So this Bloomberg and Purcell-Pound theory, and a lot of empirical measurements are supporting this kind of trend, where you have, for example, on this scale, you have increasing viscosity or molecular size, and this is parameterized by the rotational correlation time. And this is basically the time taken for tumbling or molecular rotation by 1 radian. So of course you have very short rotation times for very small molecules, but when you get to very long or large molecules, or even in the solid state, then your rotation time decreases. And it's always the case that your T2 relaxation is smaller than your T1 relaxation. So this is the parameter that is dictating the resolution, essentially, of your species in the sample. And simply, as the rotational correlation times are increasing, when you go from the small molecules to polymers to the solid state, then that means that your resolution of the species after Fourier transformation becomes worse and worse and worse. So there is, of course, two methods that are used for typically in material science and in low molecular weight chemistry. So you have solid state NMR versus liquid state NMR. Solid state NMR for cellulose is already quite well known. And of course, liquid state NMR for cellulosics is also well known, as long as you're derivatizing to such a high degree that the crystallinity isn't preventing dissolution into typical kind of deuterated molecular solvents. But here are spectra where we have actually microcrystalline cellulose without any degree of modification. On the bottom, we have our solid state NMR spectra, where we're actually retaining conformational information, where we can derive some information about crystallinity in the samples. But here you can see actually what the benefit is from running liquid state NMR, where you have very rapid tumbling in solution. So this is dissolved in ionic liquid electrolyte. And you can see that because you have much longer relaxation of the signals, then you get very, very sharp signals compared to the solid state. And that means that you can then start to resolve things, chemical species, rather than the conformational information. So these are complementary methods. In one case, you get conformational information from the solid state NMR, and from the liquid state, you get the chemical information. For solid state NMR, so this is already very well studied, and especially in Sweden, there are a lot of experts who have been developing these methods. And I think the real advantage for cellulose chemistry is determining crystallinity of samples. So these are taken from this Zuckerstatter publication or review in Lensing and Berichte, but then there are also the original articles that you can check. And essentially by peak fitting of this C4 region, which is the most common region for peak fitting, and then doing a linear combination of the different components, then you can give rough calculations for crystallinity, or you can break them down into accessible fibril surfaces, inaccessible fibril surfaces, and so on. There are various articles that I would recommend having a look at. So of course, there are several from Chalmers. So in particular, Leo Svenningson's thesis, this was really an interesting thesis. But then of course you have various other articles. And I think this lensing and perimeter review is, at least for the beginner, is quite a nice introduction. But how do we then achieve such high resolution? So we can actually start to look at the chemistry side of things. So this, I guess you're aware that last year, Herbert Sixta and Ilkka Kilpeläinen, they won the Wallenberg Prize. And this was for the development of the Ironcell technology. So that's basically air gap spinning of cellulose using ionic liquids as a direct dissolution media. So in Herbert's group, the technology was developed, but in Ilkka's group, over, I would say, a period of 10 to 15 years, we really developed a really strong experience in ionic liquids for cellulose or even wood processing. And I would say when it came to the technology development side, we had taken the approach where we wanted to develop ionic liquids that were more recyclable. So two approaches that we took were looking at acid-base combinations. So combining a super base with the organic acid that formed an ionic liquid that could dissolve cellulose. And this is one of the structures that have been proven to be very effective in the Ironcell technology. But from our perspective, we were interested in recycling the systems. And if you tune the basicity of the super base, then actually at certain temperatures, you can heat the sample up and reverse the reaction to introduce volatility based on the molecular species, and then you can recycle by distillation. But another method we had looked at was phase separation using these tetraalkyl phosphonium type structures, where you could dissolve cellulose as a ionic liquid electrolyte, but then when you add water, some of the longer chain homologs would then phase separate and you could use this as a means of recovery of the ionic liquid, preventing the buildup of impurities. So it turns out, of course, that these are rather expensive components. They are much more thermally stable and chemically stable than, for example, the imidazolium series. But cost-wise, they're a little bit difficult to work with. There's also quite considerable toxicity when you go to the very large cations. So there was not really very much motivation to continue looking at fractionation or cellulose processing methods. However, we did do quite thorough studies into the kind of ability of these solvents to dissolve cellulose. So they don't dissolve cellulose as the pure ionic liquids. So here we have the ratio of anhydroglucose unit versus ionic liquid. And I think this is with a pre-hydrolysis craft dissolving like pulp. And what we find is that when we add about 40% of DMSO, you end up getting a maximum where you can dissolve cellulose. And actually, for a lot of these structures, you will get a maximum around about 1-to-1 between the anhydroglucose unit and then the ionic, so the molar ratio of the anhydroglucose unit versus the ionic liquid. We decided to look at this is only for a few of the structures, but we actually looked at all of the structures here in this graph. And we calculated basically the saturation points at this 48% composition for all of these aliphatic homologs. So for example, 4,4,4,4 is 4 butyl chains, and I guess you get the picture for the rest of the structures. And we calculated the van der Waals volume of the cations using a computational method. And we looked at the weight percent of cellulose in the 48% DMSO solutions. And we found actually that the highest dissolving ionic liquids or electrolytes were those with the smaller cations. And above this barrier, we need DMSO in the sample to dissolve cellulose. If we don't have DMSO, we can't dissolve cellulose. But below the barrier, we have imemacetate as the most effective mixture, and actually it doesn't need DMSO to dissolve cellulose. So in my opinion, I think this is still the best dissolving ionic liquid that's in the literature, but it does have the disadvantage that it chemically reacts with cellulose. So for the purposes of running NMR, this is a no-no for us because we want to avoid introduction of artifacts in the sample. So if we go into this a little bit further and think about the viscosity of the mixtures and trying to reach a concentration that is going to give us good enough signal to noise, but still not be so viscous that we just have very broad signals, or we can't even, perhaps in some cases, get the sample into the NMR tube. So if we look here again at the weight percent of microcrystalline cellulose in solution, and the weight percent of DMSO at the saturation point. And if we look now at the anhydroglucose unit versus the ionic liquid composition, so here at about 88% DMSO, we can dissolve over 5 weight percent of at least microcrystalline cellulose into this composition. And for this P4444 acetate, we're actually getting pretty close to this 1-to-1 ratio, which means that at this point we have a very low viscosity solution, but we can still get very high, or we can get the highest amounts of cellulose into the sample. That, of course, should keep the viscosity low, give good resolution, and then give, of course, the more cellulose you have there, then the better signal to noise. If you look at phosphonium structure versus ammonium structures, so of course, ammonium compounds are much cheaper. You might think also that you could use tetraalkyl phosphonium hydroxides, which have been known in the literature as well, but these unfortunately decompose quite effectively when you increase the concentration and temperature. Also, hydroxide is going to react with a lot of components. If you look at the ammonium structures, these will decompose by Hofmann elimination quite readily. And here we have thermogravimetric analysis of the ammonium homologue versus the phosphonium homologue. And here we can see actually there's around about 150 degrees increase in stability for the maximum rate of decomposition, at least for the phosphonium structure. And when we started running NMR with these ammonium structures at similar DMSO compositions, in some cases we actually saw tributylamine forming on the surface of the solvent. So there is very good motivation to use these phosphonium structures simply because they are rather stable chemically and thermally. A little comment on the effective field strength. Of course, it's nice to have as good or strong as magnetic field as possible. So you basically do have a relationship between the signal to noise and the field strength. So two field strengths are related by the second divided by the first to the power of 1.5. So that means that actually if you start with a 300 megahertz spectrometer and you go up to let's say 800, you've got 4 to 5 times the signal to noise. I would say the resolution is maybe more important. So here we have a series where we've run microcrystalline cellulose, and this is in a 500 to 850 megahertz spectrometers. And you can see that there is definitely an increase in resolution here, but then we were happy enough to be able to run a sample through Wim Thielemann in Lille or KU Leuven. They have a 1.2 gigahertz spectrometer, and with one scan and a 3 millimeter probe, you can see that we get really excellent resolution. So I would say this is of course not available to everybody, but you're starting to get to levels where, I mean, the processing of the spectra starts to become considerably easier as opposed to using integration versus peak fitting to process the data. But I mean, you can still get really excellent resolution on a 500 or 600 megahertz spectrometer, which is the type of spectrometer that you will find in pretty much every university lab. Temperature is important. So this is just to show the effective temperature. And here we have proton spectra of microcrystalline cellulose going from 15 degrees to 65 degrees. And I hope this works. Okay. I don't quite know how to get it to work, but
I think if you, I saw the laser point. If you go back where you
yes,
were, and the laser pointer
Start with-
up there.
Okay.
Yeah.
Okay, so okay, but it seems not to be working on this computer, but essentially you see an increase in resolution with temperature. With proton versus carbon, so these are the two most useful nuclides when it comes to analyzing cellulose. In one hand, with proton, you get really excellent signal to noise. So this is 32 scans, which takes about 1 minute, but you can see that actually the resolution is rather poor. If you want to run carbon, the resolution is much, much better, but then your signal to noise is really very poor. So here's 5,000 scans, which is taking about 2.5 hours. And you can see here that you have a very considerable noise in the sample. So ideally, you want to get away with running Proton NMR, which is easier to implement as a quantitative experiment, but you suffer by having poor resolution. So one way that we get around of this is simply by using peak fitting, similar to which is used in the solid-state NMR, provided, of course, you get good enough resolution of your species. And of course, if the problem persists and you can't really separate species, then of course you can resort to doing carbon NMR, quantitative carbon. And typically you can get quite good signal to noise overnight with quantitative conditions. But of course it consumes a lot more spectrometer time. So I guess this is one way to resolve spectra by going to carbon NMR, but of course the collection or acquisition times are really very long. But to assign species in, for example, proton spectra for peak fitting, you can rely on higher resolution experiments such as 2D experiments, where you're taking advantage of both the carbon and the proton dimensions to separate species. And these are proton detected experiments. So you get already good signal to noise. And here is an example of a cellulose sample, which has a degree of polymerization of around about, I think it's around about 15 actually. And you can see here that actually here's our acetal region, and this is our CH1 correlation. And you can actually separate the alpha and beta anomers from the reducing end, and then this is the non-reducing end signal. These are all separable, and actually you can assign the rest of the peaks in these reducing end and non-reducing end signals. So you can get really excellent resolution by applying 2D NMR. This is your typical 1D spectra, and you can immediately see this is our saccharide region. And even at approximately 1:1 molar ratio of ionic liquid to the anhydrous glucose unit, you still have these very large aliphatic signals that are in the proton spectra. And you can imagine that if you're attaching some species like fatty acid chain, then actually these are in superposition with the alkyl positions, and you may not easily be able to see them or integrate them or peak fit them. So one method that we also apply as a kind of a standard method is diffusion editing, which is essentially a 1D DOSY experiment. And for a typical DOSY experiment, you apply, so this is a method that's used to separate species based on their self-diffusion coefficients. So in a typical DOSY experiment, you run a gradient array where you have increase in gradient strength. And at the start of that array, you're not really attenuating any of the signals. But as you start increasing the gradient strength, then those lower molecular weight, faster diffusing species, they attenuate from the spectra much, much faster than the higher molecular weight species. So for example, this is the H1 peak in cellulose, and this is one of the aliphatic signals on the ionic liquid portion, which is, of course, is much lower molecular weight than the actual cellulose molecule itself. So what we do is we can choose simply a point out of this array where we have attenuated our signal to zero essentially. And then we retain our polymeric species in solution or in the spectra. And here's an example of what I mean. So this is the proton spectra on top. We have water here. We have our cellulose backbone aliphatics, our CHs. We have DMSO, residual DMSO, and then we have our alkyl positions from the ionic liquid. And when you carry out the diffusion editing, essentially you can eliminate all of these slow diffusing species from the spectra. So you have your cellulose retained here, and you get some small artifacts remaining from peak cancellation during this 1D dozy experiment. So you can imagine here, if you have modified cellulose with some low or to a low degree of substitution, some aliphatic containing moiety, then if it's attached to cellulose, it will diffuse at the same speed. Therefore, it will not be attenuated from the spectra. Just a quick overview of the types of experiments for resolving using 2D or correlation experiments. So we have HSQC. So this is basically a one bond correlation experiment where you have coupling between proton and C13. And essentially you get a correlation in your proton and your carbon dimension. This is a kind of a bread and butter experiment in organic chemistry. And of course, we've seen how this can lead to very high resolution and separation of components. There is also HMBC, which is a longer distance proton carbon proton C13 coupling experiment or correlation experiment. And you can see here, for example, your 1 position in the carbon dimension is correlating with the 2 position, but also you can see longer distance correlations. And here we see the 4 position. I would say this is not really very valuable when it comes to cellulose assignment of cellulosic components, simply because relaxation, essentially the signal to noise in HMBC experiment is suffers rather badly when you have poorly mobile species. But what it is quite useful for is looking for correlations between carbonyl signals and then other species on some other appended functionality, or perhaps even to the aliphatic chain or to the cellulose backbone. For proton-proton correlation, you typically would apply a COSY experiment, but another variation of this is a TOXI experiment. So this is a multiple bond proton-proton coupling experiment where you can essentially see couplings throughout the chain, depending on the mixing time. But I would say that these have, of course, they offer higher resolution, but they don't offer really, you can separate species using this method, but there are limitations. But what I think we've found is what is more preferred is actually employing a HSQC TOXI experiment where you're taking advantage of both the resolution in the carbon dimension for these correlations, for assigning correlations, and the proton. So here, for example, you can see the 1 position is, of course, next to the 2 position, but then you get this correlation based on the TOXI coupling between the 1 and the 2. And depending on mixing time, you can see further along this chain. But we've, I would say, optimized this so that we get COSY-like correlations to maintain signal to noise and take advantage of the resolution in the carbon dimension. So I would like to give one quick example of where we've used this, and this is in the analysis of reducing end groups. So analysis of chemical modifications at reducing end groups. And there is this recent review that has been published that goes into this in quite a lot of detail. And we have a couple of articles that I will show on the next slide. But this is a rather, I would say, rather large challenge, is to confirm that you actually have reaction at reducing end groups, and then try and understand a little bit more about the chemistry or the mechanisms of reactions at reducing end groups. And the typical methods that have been used for analysis of nanocelluloses that have been modified at reducing ends are these kind of indirect methods. So So spectrophotometric quantitation is typically used where you might carry out a reaction and then you quantify the availability of aldehydes before and after the reaction. So that is an indication of how effective the reaction has been. And there's a list of different methods that have been used in this review article. Then you also have these kind of reducing end functionalization and combining that with microscopy. And I would say the classical example are those methods that have been developed by Sujiyama, where they have taken nanocrystals, either non-mercerized or mercerized, and then reacted to form nanoparticles. I think it's silver or gold nanoparticles at the end of where you have reactions at reducing end groups using a linker. And then this can be combined with microscopy to see the effect of mercerization or essentially where the reducing end groups are. And also in combination with electron diffraction to identify the allomorphs that are present in the samples. So this is a really fascinating way of doing this, but it's not a direct method of measuring reactivity at the reducing end. It's not really a direct method of quantifying, although that is still a challenge for NMR. And it's not really telling us anything about the kind of chemistry that's going on, only really what we know on paper. So we have two previous articles looking at this. One is confirming canonical condensation for modifying reducing end groups. This is published a number of years ago by Katja Heise. Then we also have another article which is published a few years ago by Gwendolyn Delpieri, where we're also confirming reductive amination at reducing end groups, and then the further kind of ATRP modification by grafting on this polystyrene sulfonate group. I don't want to go into these today, so I would like to present some new results that we have looking at glycosylamine formation at reducing end groups. So, of course, reductive amination is a really classical method now for functionalizing reducing end groups. And typically you start, of course, with your classical chemistry for saccharide chemistry. You have your alpha and beta form of your glycosol residues or glucose residues. So these are in equilibrium with the alpha and beta form, and then you have a minor form, which is the aldehyde form. And if you want to carry out reductive amination, you add your reducing agent, where you get this kind of intermediate shift base form, and then you add a reducing agent, or sorry, you add your amine to get this shift base form, and then you add a reducing agent to convert this to the glucamine form. And these are all rather hydrolytically unstable. This is well understood from the literature. But what is also well understood is that you can actually get these stable glycosylamines, which also have alpha and beta anomers. And then also if you treat these samples at higher temperature or variation of pH conditions, catalytic conditions, then you can further convert these via Amador rearrangement or further with Maillard cascade reactions. So we wanted to really look and see if we could actually avoid the use of reducing agent, so for functionalization of reducing ends in cellulose nanocrystals, because typically the reducing agents are used in really large excess, and this is not really a sustainable method of converting these materials. So we started by making models, and we looked at a few different primary amines. We started with butylamine, going up to dodecylamine, and we found that actually the dodecylamine reactions seem to form stable products. So we have characterized these using glucose as a model. We've also carried out reductive amination with this picoline containing reducing agent, so it's something similar to picoline borean. So then now we actually have assignments for these compounds to compare with modification of reducing end groups in nanocellulose, cellulose nanocrystals. You can see here from this spectra that actually you do see very clearly these glucosylamine anomers. You can assign these geminal positions So for example, these alpha positions, and then of course, these are our geminal positions for the 6th position. These are all rather diagnostic when it comes to looking at the 2D spectra of modified celluloses to indicate that we have a reaction. I would say the most diagnostic signals, of course, are our aliphatic signals, but then we have our geminal positions, and then we have these anomers, and the presence of these anomers would indicate a successful reaction. So there's a lot of literature on glucosylamines, and there's of course NMR assignments for these kinds of compounds, but I would say a lot of these assignments are based on solution-state NMR, and there's no guarantee that they're stable in the solid state. So in this case, we've compared the solution-state C13 NMR with this should be solid-state C13 CP mass NMR of this anomeric mixture. And what we find is actually this glucosylamine is stable in both the liquid state and the solid state. So we can expect that if we modify reducing end groups that they should exist as a glucosylamine in the solid state and liquid state. If we carry out our diffusion editing on the reacted CNCs, so we can eliminate, essentially, these are artifacts from the ionic liquid. So we carried out a reaction in water, and these are using commercial CNCs where we had an excess of dodecylamine. So we carried out a reaction in water and in DMSO. We can clearly see the retention of these aliphatic signals in the spectra, which clearly correspond to modification of the reducing end groups of the nanocrystals, simply because these aliphatic signals are retained in the spectra, and there's no opportunity for them to polymerize. So the only way they can have the similar diffusion, self-diffusion coefficients is by covalent attachment to the cellulose. And if we then run 2D NMR, so we had to go to a cryoprobe to get this spectra, but we can see clearly that there are these glucosylamine anomeric positions left in the sample. What is interesting is that we can also see, so this is just the 3D representation here. So these are the glucosylamine peaks, but we also see some of the reducing end anomers left behind. So based on this spectra, we can estimate that there's approximately about an 80% conversion. So the reaction isn't going to completion, but we have, the sample has reacted to a large degree. When we carried out this reaction on when we carried out this reaction on the same material which has been reacted with the reducing agent, we actually don't see any of the glucosylamine peaks or the reducing ends, which is kind of indicating to us that the reducing ends themselves are reacting faster than the shift base. Yeah, so I guess this is the last slide. So this method is actually reaching publication. So we have a Nature Protocol article that should be published in 2 or 3 weeks. I'm not totally sure about this, but at least we have a DOI at the moment. It's not online yet. So this was compiled by Lucas Fleary and Michael Hummel's group, and it's really a very extensive article, and it's designed as a method to kind of for the non-expert, essentially, to give a good indication how to use this method. So I would really recommend reading this if you want to start using this method. So to conclude, I would say that solution-state NMR has been really a mainstream technique in synthetic chemistry since 1960s, essentially when spectrometers have been commercialized. But now it's actually possible to apply these similar kind of analytical standards to cellulosics. I would say that this is not something that's going to replace solid-state NMR. I think they give very complementary information. And I think really NMR for many people is kind of considered as like an analytical technique, or people are rather afraid of it. They consider it as a black box. But whenever this Nature Protocols article is published, then I think this will be very valuable in kind of opening this box a little bit. So I think definitely if you want advice on how to use this method, just please contact us. And I think to acknowledge most of the work has been done in University of Helsinki, but also with Aalto University. Also some recent experiments with Wim Thielman and KU Leuven and a few other institutes. And those that have done the most work on development of the method have been Tatjana Koso, so Jingwen Jia, Lucas Fleary, Katja Valtteri Makela, and Ashley Holding. And this has been a long-term funded project where NMR is not the focus of the projects, but more kind of technology processing of biomass. So that is it, and I would be happy to take questions.
Thank you a lot. So Alexander and me will try to help each other to direct questions to you.
Mm-hmm.
It was a fantastic nice talk. I was super inspired of it, and I learned a lot. I think we have one question in the chat. Alexander, do you want to read it?
For some reason, I cannot see it, Josephine. It disappeared for me.
It disappeared for me as well.
Yeah, it's not here either.
So the one who
should I stop sharing? Would it help at all?
No, I don't think so. I think it was
okay.
Celine. Or is it
Yeah,
Celine that asked it?
So you who wrote the question, you can raise your hand or type it again if you want. But we have a raised hand from Lasse Evenes.
Oh, nice.
So I can allow you to talk.
Hi, Alistair. Thanks a lot.
Hi.
Very nice talk. I hope you don't mind if I took some screenshots for my teaching.
No problem. I can send you the presentation. It's no problem.
Very nice. I have one question. You showed a very nice slide where you compared, I think it's where you compared the spectra from different field strengths.
Yes.
And I guess, yeah, it was, yes, this one. And the three first is the same material, right? It's the MCC.
Yeah. So we haven't run MCC on this 1.2 gigahertz, unfortunately.
So I have a question. My first question is more these smaller peaks around C1,
yes.
I guess, what those are. Maybe you said it that I...
Yes. So this is the non-reducing end H1.
Mm-hmm.
This is the beta anomer, and this is the alpha anomer.
Okay.
And then because these are CNCs from sulfuric acid digestion, we also see this geminal 6 sulfate half esters here and here. I had another slide where we had different types of pulp, and you can get rather good separation of these peaks for the different like one positions for the different hemicellulose.
My main question was more about if you take, like, say, the 500 megahertz and you go into the C25, C35 region,
yeah,
where it seems like you have some, for the two first peaks, you have like 2 or 3 peaks included. I mean, you have like overlapping peaks, it looks like.
Yes.
In the C, like at 3.4 ppm roughly. Yeah, exactly.
Yeah.
So in the at 500 megahertz, it looks like a bit you have 2 peaks on the first signal and maybe, or 2 signals on the first peak and maybe 3 signals on the second peak.
Yeah.
But on the high field, it looks much more isotropic.
Yeah. So I don't know is this because of the kind of the higher field, the couplings are changing.
So I was more surprised because I was thinking at the lowest spectrum,
yeah,
this kind of it's not just broadening, it looks a bit like you have several signals down there, right?
Yeah, for sure. Yeah. So I'm not so sure.
Mm.
Yeah, I mean, it's hard to say.
Or is it some kind of decoupling effect due to the
I think it's
field strength?
I think it's due to the field strength. You can notice here as well for the lower field that actually this looks like a small doublet here, and then when you're going to higher field, it increases.
But that means it's a bit you can be a bit fooled at the lower strength then, or
yes,
that you have more. You don't have all the. I would get fooled and think that I have more different structures or something.
Yeah, so it depends how much you want to kind of read into the information that's presented, and sometimes when we do this peak fitting, we would actually, you know, increase the adipozation, so we would get like broader signals, so that it's easier to separate components.
Okay.
So yeah.
And then my question was on you showed a comparison of the proton and carbon.
Yes.
And you said to like 2.5 hours for the number 20 there, I think it was.
Yes.
Is the carbon run under just a routine instrument, or is this a high field instrument?
I think this was on a smart probe, which should be
okay.
I think it should be optimized for carbon. But I mean, you can of course get much better signal to noise if you use like cryoprobe optimization, optimized for carbon, or I mean, it is possible to get better signal to noise.
I mean, that's I would think this is pretty decent, right?
Yeah.
If you're concerning the probe and the magnet that you are using here.
Yeah, for sure. I mean, it's not so bad, but I don't think this was a quantitative experiment, at least. So, I mean, we've calculated the T1 values for quantitative carbon, and at least for the cellulose backbone signals, if you have, what did we calculate? I think we determined that if you have maybe 30-degree pulse, you can have a relaxation delay of 5 to 6 seconds. So not that much longer than the standard kind of a carbon experiment. So an overnight experiment is very often, if you have high enough degree of substitution or a chemical modification, it's enough to give you good enough signal to noise in separating components. But then, of course, a lot of the error comes in the kind of integration and where you place the boundaries. So,
cool.
So yeah, if you have the spectrometer time available, then very often you can get decent signal to noise in a week. So.
Okay. Well, thank you a lot, Alistair. A very informative talk you gave.
Yes, thank you.
So, do you see any questions in the chat, Alexander?
Yes, so we have one now, and it's a question then from Celine Larsen. And she says that they're considering the ionic liquid method and are wondering what sample concentration of cellulose in P444 with the DMSO would you suggest? And would there be any overlap between the ionic liquid signals and the cellulose?
So for Proton NMR, there is no real overlap, except when it comes to the aliphatic signals. But that's why we would apply the diffusion editing experiment as a kind of a positive confirmation of reaction. When it comes to the concentrations, so I mean, we have 80% DMSO, deuterated DMSO, about 20% of the ionic liquid. And into that electrolyte solution, we would put, typically for cellulose nanocrystals, we would put something like 5 weight% of the cellulose. The molecular weight of CNCs or even so CNF is rather low, so that we can still get low enough viscosity and decent resolution. But if you then move to pulp, chemical pulp samples that have considerably higher molecular weight, then I would really not go much above 2 weight% or 2.5 weight% for the dry weight of the cellulose. Otherwise, you will start to actually get into trouble transferring the sample into your NMR tube. And of course, you will have broader signals. But still, you get quite good signal to noise. So you just need to use, depending on the chemical modification, then you would need to use 2D methods to assign peaks or to try and, or using diffusion editing or peak fitting to try and separate peaks if they're overlapping with your aliphatic signals. I hope that answers the question.
Yeah,
seems so from the chat.
Okay.
Diana here has a question. Hey, thanks so much. It's really nice to see all these NMR spectra since, as Annette said before, I'm an NMR nerd. I only wondered, since you have phosphorus there, and I wondered if you have measured some HOSI, or if you have looked into how these ions containing phosphorus interact with the cellulose. Was this maybe an interest?
Well, yeah, so I haven't tried to do that. So I think the actual, I mean, you have this kind of tetrahedral geometry around the phosphorus where you have these aliphatic chains that prevent very kind of close interaction with the phosphorus. So I'm guessing that the distance is simply too far to get this kind of NOE type interaction. But I've never tried, to be honest. That could be something that could be interesting to try. But I mean, looking at NOE between the aliphatic signals could be also something that could be tested.
Yeah, because if you look at slide 23 and I look at the diffusion edited spectrum, it looks to me that there is, so to the spectra to the left, there is some kind of fraction that is really slow diffusing. That is.
Yes.
To me, this would maybe indicate that there is one, like free, and then there is one part
that is complexed to the cellulose. Yeah, it's quite possible. And I can't remember exactly the conditions that I used for this experiment, but it may also be somehow artifact of the DOSI experiment that we don't get full attenuation of the signal.
Yeah.
But yeah, it's quite possible. And I remember from a number of years ago, some articles or some presentations by Thomas Rosenau where they had looked at complexation of different kind of imidazolium ionic liquids with cellulose, and they had suggested using these various correlation experiments that there was a very kind of strong first solvation shell that's formed. So it may well be. But I would say, I mean, please try it if you're interested in doing it. So.
Because this would lead me to my last question. I'm not sure if you actually explained that, but you said you have to add DMSO at some point, if I understood you correctly.
Yes.
Do you know the reason? I mean, what is why do you need to add DMSO to dissolve?
Yeah, so
more, I think it was.
So based on like some molecular dynamics simulations, I can't remember who did them. They were looking at the kind of interaction energies between ionic liquid anion and cation with kind of cellulose crystallite model surfaces. And they had found that with co-solvents such as DMSO, so a dipolar aprotic co-solvent that doesn't hydrogen bond, this allows for better anion-cation pair separation, which allowed for a stronger complexation with the cellulose. So it seems that it might really be related to separation of anion and cation pair, because with phosphorus you have a very strong point charge. And okay, with acetate you have a small distribution of charge, but of course if they have some kind of a preferred conformation where you get like the acetate fitting in a kind of a groove, then of course the coulombic interaction can be rather strong. And I think the addition of the dipolar aprotic solvent helps to kind of separate these components. This is a very kind of basic explanation, but there is some evidence in the literature for this.
Okay, thanks so much.
Okay, thanks.
And thank you so much for all of you. Thank you for a very nice presentation. We unfortunately have to stop there for the will be other more internal meetings. But thank you all. And Annette, there will be more fiber webinars coming up. So that will be announced on the Treesearch website, where you also can find a link to the fiber website, or if you go directly to cellulose.se. So thank you, and hope to see you again.
Yeah.
Thank you.
Thank you a lot. Thank you. Fantastic. Alistair, I hope we can meet and talk more another time.